Okay, let's get started. We, uh, we're in the world of graph algorithms. Any questions about homework or graph algorithms or anything that people want to start with first? Logistical things, anything like that. Okay, so last class, we're now in a world of weighted graphs from last time. We're in a world of computing minimum spanning trees. And the problem of the day is a problem on, suppose I am giving you the minimum spanning tree of a graph. So I am given a world where I have, someone has given me the minimum spanning tree of a graph. And let's make another edge there just for the sake of it. And there probably are other edges in the graph. Let's say I'm going to put these here that were not part of the spanning tree. Okay? So I'm given a graph with n vertices and m edges. I am given the minimum spanning tree, which is in red. And I am given, dramatically, a new edge. Okay? How do we compute the minimum spanning tree of the old graph G plus the new edge? Okay, efficiently. Does everybody get to see that? You have a graph, you have the minimum spanning tree of the graph, and you've got a new edge that's being inserted. Okay? Can you give an order n algorithm to find the minimum spanning tree of the new graph? Any questions? Any ideas? Yes?
We could look at the two vertices you would meet, and then get all of the edges that are incident on you and me that are in the minimum spanning tree. Check among those for which has the maximum weight. If the maximum weighted edge has a greater weight than the edge that we're incorporating, incorporate that edge, remove the maximum.
Okay, so what I'm hearing you say, which is sort of, well, let's just think what you're saying. What I think I heard you say, and you're allowed to change it, is we take a look at the red is our current spanning tree, minimum spanning tree. We're going to add a, an edge, and then we're going to look at the edges near that touch on the tree edges that touch on that minimum spanning tree. Okay, and what are you going to do with that? Find the maximum weight edge there. Okay, and what you're telling me is if you want to delete the largest weight vertex edge of these blue edges, these blue dotted edges. Okay? So I don't like that algorithm for a couple of reasons. Why don't I like it? Well, first of all, suppose the edge weight of this was 100, and the edge weight of this was 6. Would we be better off deleting the edge that was of weight 100 to add the edge weight of 6? The cost will go down, it's cheaper, but what's going to happen? That vertex is isolated. We no longer have a minimum spanning tree, right? We don't have a spanning tree. Okay? Now let's say I don't consider it. Suppose, let's say, let me see if I can do this. Suppose the weight of this one was 3. And the weight of that one was 2. Is it clear that that edge 6, the black edge, can I delete that now? Or might it still be on the minimum spanning tree? Think about it. Yeah?
It might still be on it because there's this cycle, so you can delete
the word that I wanted to hear was the word cycle, okay? The important thing was not what edges were touching that new one, but if this edge over here had a weight of 100, then we would be happy to replace that edge with the new one added. What is the interesting property? If we take a spanning tree, particularly the minimum spanning tree of what we had before, and we add an edge, what's going to happen? We're going to create a cycle. And the important point here is that we could delete any edge. Let's now get this down to the point where I just have a tree. I think I'm doing a really careful deletion job here. Look at that. Whoosh. Now I've got a cycle. It should be clear that I can delete any one of those edges on that cycle, and I will still have a spanning tree. Does everybody agree with that? Which is the edge that I want to do? Which is the edge I want to delete? Like you said, I want to delete the biggest one, right? How do I find what are the edges on the cycle and what the biggest one of them is? I'd like to do that in order and time. Okay? Any ideas how I can do that? Yes? You're saying do a depth first search excluding that edge, and what? Find the shortest path from U to V. So what you're saying is do a traversal of the red tree. If I started here, maybe it would look like this. Conjunct, 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 conjunct. And then what you might be saying is, if I have a black edge that I'm adding, find the shortest path from here to there. That might be there. Okay? This still seems I didn't make too much progress. What would I do? I would do a depth first traversal of it with the new edge in. Now, what would happen if I did a DFS with the black edge in? Everything is either going to be a tree edge, if it's an undirected graph, or it's going to be a back edge. Okay? And once I have a back edge, then the back edge with everything that it takes to get to that point, ka-chunk, 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 I can walk up the parent thing and find what the edges on that path are. Does everybody agree with that? So now if I did a depth first search, okay, and for every edge of discovery, let's say I keep track of the weight of the edge, okay? So long as I can, actually, so long as I have a pointer to the edge record that has the weight, okay, I can now go through for every one of these edges and find what their weight is. The one that is the biggest of this, and this is going to be, is going to be the edge that I want to delete to create the minimum spanning tree. Any questions about that? People see how that kind of works? Okay. The important thing is that this idea of cycles and that adding an edge to a tree creates a cycle, that was what was the crucial thing in the proof of correctness of Prim's algorithm. What was Prim's algorithm? Prim's algorithm for finding the minimum spanning tree. We started a vertex. We took a graph. We started from some vertex t. In each iteration, we are going to go and find what is the smallest cost edge between something in the tree and something that isn't. Okay? Then we're going to go around again, find the smallest cost edge between something that's in the tree versus something that isn't. Keep going. We're going to grow a spanning tree this way. We can't add an edge to something already in the tree because that creates a cycle, right? But this is the algorithm that we're doing, okay? Any questions? And what was the correctness argument? This is what I talked about last time. Why is Prim's algorithm correct? The proof was by contradiction. Suppose it isn't. Then there is a graph where Prim's algorithm does something wrong, meaning it produces a tree that is not of minimum weight. If so, let's run Prim's algorithm on that graph, and there will come a moment in time when you're going to add an edge, shown here in red, that irrevocably there is no way to take what's currently in the tree and that new edge and come up with a minimum weight spanning tree. That's what Prim's wants to do. Prim wanted to add that edge. You're telling me, no, this is a counterexample, it doesn't work. And I'm going to say, oh, well, at the time I added this edge, it would not have created a cycle. Let me add that edge to whatever spanning tree you come up with. It's going to create a cycle. Now, X was already in the tree, Y is not in the tree. So there is going to be a cycle created that will go, which if we edge X, Y was the critical edge, where Y, there's a path from Y that gets back to the critical, back to a vertex that was in the tree. And you tell me that this was the minimum spanning tree? Note that this edge over here was an edge that crossed from outside the tree to back inside the tree. Back outside the tree that we had already built up to the point where we tried to insert this, to a vertex that was in the tree at that point. Such an edge has to exist. And what do we know? We know that Prim's took the cheapest such edge. So if that's true, deleting this edge from your tree and adding my edge will still be connected. It's not going to have any cycles, and it's still going to be connected. And the cost of doing this can only lower the cost of the tree. So therefore, I could not have gone wrong, okay, picking this edge in the first place. That's the contradiction. And that's why Prim's is correct. Any questions about that? Okay, good. Let's check one other thing. And again, that's what I'm describing here on the slide, but I think hopefully you got. Any questions about the correctness proof? What is the speed of Prim's algorithm? Okay, Prim's algorithm started from an arbitrary vertex. While there are not tree vertices, find the cheapest weight edge between the tree and what's outside there, okay, that we're growing. And then add that edge and vertex to the tree. How many times will this outer loop go around in the obvious implementation if there are n vertices and m edges? How much time will that go around? Someone with a hand? Yes? Well, how many will the outer loop go around? How many non-tree vertices, while there's non-tree vertices, how many times will that loop go around? N, because we're going to do that once for every vertex. What's it going to cost to go through all the vertices, all the edges, and find the minimum weight edge that goes between a vertex and the tree? You're saying it's going to take order m. It does look like we got to go through all m edges, right? How will you tell in constant time per edge, though, whether a vertex is in the, whether one of the vertices is in the tree and one of them isn't in the tree. Do we see that that's something we got to do? It's not enough to know that this edge is of weight 6. It goes between y and q, okay? But we need to know that this is one that is going to increase the size of my tree. It's not going to do something like that, meaning a disconnected thing, and it's not going to do something like that to create a cycle. How can we quickly tell whether an edge is in the tree or an edge is going to have one vertex in and one vertex out? We need to be able to do this in constant time if it's going to run in order m time, as you'll agree. Is there a data structure you can imagine that would make that kind of implementation possible? Okay, how? Hash table. You could conceivably have a data structure, a hash of all the vertices that are in the tree. And say, I'll look up one, I want to know about edge YQ. Is Y in the hash table? Yes. Is Q in the hash table? No. That's one way you might do that. But I don't like that actually, because that's not, is that worst case constant time? You could get unlucky. So the hash table is actually overkill and not as good a way to do it. How would I do it? I would have a Boolean array. You want to know whether edge xy is legal. What if I have a Boolean array in tree and vertex I is going to have a 1 here if it's in the tree and a 0 if it's not? Does everybody agree? Now I can just look up what's the value of, is intree of x equal to intree of y? If they're not equal, then one is in and one is out. Okay? Any questions? You see how I use this bit vector idea to do that test? If you do that, we can do this in a total of nm time to find Prim's algorithm. Any questions? Now, in fact, we would like to be able to do faster than n times m time. And the question is there a way to do this part faster? Okay, is there a faster way to tell whether or not, find the minimum weight edge linking a tree vertex to a non-tree vertex? The answer is, let's use a data structure to keep track of these things. Okay, so here is, in order to do it faster, we have to be able to identify what are the fringe vertices, the ones that are within a distance of 1, one edge from being in the tree, and the cheapest way to get to it. So what is the implementation of Prim's algorithm going to look like? I'm going to claim I can do it in order n squared time. And I want you to look at my implementation. Okay, I'm doing a Prim's. I'm starting from a particular start vertex. What are my data structures? I'm going to have that Boolean vector I just talked about in tree, which is going to keep track of true or false. Is vertex I in the tree yet? Okay? Distance is going to be what is the cheapest way I know of to get vertex I into the tree. Okay? Every vertex is either going to be in the tree or there is a cheapest way I know about so far to get it in the tree. Okay, that's what the distance vector is going to keep track of. And the total weight of my tree, I'm going to keep track of as well. So what is my Prim's algorithm? Initially, for every vertex, is it in the tree? No, it's not in the tree. What's the distance to get vertex I into the tree? Well, right now I don't know anything at all. It's infinite cost to get you into the tree. If the graph was disconnected, what's the cost of getting you into the tree? It would be infinite. So that's what I'm initializing it to. And parent is going to be like in my tree of discovery, who was the one who let me into the tree? Okay? That was what was necessary. We used that in BFS and DFS to maintain that tree thing. What is my next thing? For the start vertex, I'm going to claim that the distance to the start vertex is going to be 0. And in general, let's say V is the last vertex that we want, the next vertex we want to add to the tree. So what is the loop, the key loop in Prim's algorithm? Okay, I wish I had this thing. Let's start it here. While V is not in the tree, which was certainly the case at true, we're going to add it to the tree, and then look at what the consequences are. Okay? Well, first of all, if I'm adding a vertex to the tree, okay, I may want to print out what edge was the edge that got it there. In general, the edge that got V into the tree is the parent of V, okay, going to V, okay? This is kind of the update, okay? In general, except for the start vertex, what was the cost of adding it to the tree? Nothing, it's a start. In general, trees get, there's n vertices, n minus 1 additions of vertices, and we will deal with that. Okay? What is my next step? I'm going to take a look at all the outgoing edges of V. Okay? If V is now in the tree, putting V in the tree means that anything that is adjacent to V, there is a new way of getting that guy into the tree. My distance metric was supposed to keep track of the cheapest way of getting it into the tree. So how do I update it? I'm going to go through all the outgoing edges of V, the adjacency list representation, and if I have an edge Vy of weight W, under what conditions will I want to deal with it? No, actually, it looks like it's VW is the name. W is the name of the other vertex here in my code. Maybe that's kind of ugly. What is it saying? What P points to dot weight is the weight of the edge. Okay? If the distance, the best way I already know to get vertex W into the tree is greater than the weight of the edge, okay, then that means that the weight of this edge is a cheaper way of getting it in. If W is not already in the tree, and I found a cheaper way to get it into the tree, then I need to update my data structure. Namely, the cheapest way to get W into the tree is now that new edge, YW, VW, and the parent of W is going to be V. This thing updates the cost of having added V to the tree. What is the cheapest way to get to all other vertices through V? If it's cheaper than the best way I know of adding it, I'm going to keep track of that. Any questions about that? What is the running time of this chunk of the algorithm? Yes? This is the order of the degree, actually. Is this the order of the degree? Yeah, I'll give it to you. That's the running time of the degree of V. Okay? Which might be n, might be less, right? Okay. What's the next part of the algorithm? And here's where I regret the way the slide rolls. What is this part of it? Now that Prim's algorithm, now that I've updated the cost, the vertex we're going to add to the tree next is the cheapest vertex, the vertex that is closest, the lowest way of adding it. What does that mean? We're going to go through all vertices, okay? And we're going to ask if VI is not in the tree, okay, and the distance to I is basically less than the cheapest edge I know of between a vertex not in the tree and one in the tree, I'm going to keep track of it. Does everybody see what this is doing? This is sweeping through that distance array and going to tell us what is the cheapest edge vertex to add. So what is this doing? Up here we had a data structure we were updating. Over here, we're now going to find the next vertex V to add. What's the cost of this part down here? What is the cost of this time? O of n. And what was the thing? We had an outer loop here that was going around how many times? Let's take a look at it. Boom. While not in tree, we're going to go through one iteration for every vertex in the thing. It's going to go around n minus 1 times. N times n. This is an order n squared implementation of Prim's algorithm. Any questions about that? So instead of scanning through all the edges every time we want to find the cheapest one to add, we're only going to scan through the edges that could possibly be the cheapest one to add, which is namely the cheapest way to get to any vertex that we know of so far, to get to every vertex that is not in the tree yet. Any questions about that? Yes. How does this avoid cycles? Okay? Well, let's think about it. A cycle would happen under what condition? It would happen if we added a vertex that was already in the tree. Right? So how are we avoiding cycles? Well, look at what we're doing within trees. We're only adding vertices here that were not yet in the tree. So we're not going to add another vertex twice. But probably more important to scan is here. What vertex do we want to consider? Only those vertices that are not in the tree are we considering as candidates to get in. The way we avoid cycles is we never add somebody into the graph that was an edge to add somebody in who was already in the tree. And that's the prerequisite to make sure there's a cycle. If I start from here, then every edge has to go to a new vertex. Okay, I can't create a cycle. I can only create a cycle with an edge that goes to an old vertex. Okay, one that was already in there. Any questions? Okay, so what do I want you to see from this? I want you to see why Prim's algorithm is correct, and I want you to see why it is n squared. Okay? Because that's actually the thing that is clever here, is the use of data structures to avoid going through the search of all, of all the edges on each iteration. We're only going through the edges that could possibly be the cheapest, okay? Any questions about that? And that is why Prim's algorithm is n squared. Okay? Okay, any questions about that? Okay, what is the worst case running time that we could hope for? Is n squared good or bad to compute the minimum spanning tree on a graph of n nodes? Should we hope for a better graph algorithm, or should we not be able to hope for a better algorithm? What was that? Someone? Okay? Why should we hope for a better algorithm? First thing I'd like to tell you is, on some level, if the graph is dense, I'm very, very satisfied with this. What if you gave me an input array, if it was an n by n graph that was completely dense? Every pair of vertices had a distance between them, right? Then that's got n squared edges on it, right? If you give me a general matrix of n squared distances and say build the minimum spanning tree, can I hope to find the minimum spanning tree without looking at every element of the matrix? I would like to say no. What if I told you that the weight of edge ij was minus 1 billion? Does everybody kind of see that? If so, that's something I want in my minimum spanning tree. It should be clear that if I had a very dense graph, okay, I've got to look at every element in that dense graph. Okay? And so n squared is as good as I can hope on a dense graph. Does everybody see it? What is the performance of breadth first search on a graph that's dense? Suppose I give you a very dense graph, a complete graph. What's the time that breadth first search is going to take on it? It was going to take order n plus m. What is m going to be on a dense graph? N squared. Does everybody see that it would take just this much time to do breadth first search or depth first search on a dense graph? So if you give me a dense graph, Prim's algorithm looks great. Does everybody agree? Now what if I don't give you a dense graph? If I don't give you a dense graph, it's perfectly reasonable to talk about something that has a linear number of edges and want to find the minimum spanning tree. Okay? So there is another algorithm called Kruskal's algorithm that is another way of computing minimum spanning tree. And this one has the advantage that it is faster on sparse graphs. Okay? It is like Prim's, a greedy algorithm, okay, in that it's always adding a small edge, but Kruskal's algorithm does not demand that we grow a tree from one point, okay? Kruskal's algorithm is going to look at all the edges of the graph and add the cheapest one that does not create a cycle. Okay, let's take a look at this more carefully. Okay, so here was our, here was our practice graph. What is the cheapest edge in this graph? What? 2? So we should add an edge of weight 2. Which one do you want to add? I'm just going to be consistent with my example here. I'm going to add that as my first edge, right? Now, what is the cheapest edge in the graph? 2. What is the cheapest edge in the graph? 3. Hey, it looks like I'm kind of growing a tree. I don't like that so much. What is the cheapest edge in the graph? 4. What about this edge? That weighs 4. Am I happy with that edge? I am not happy with that edge. Why? Because it's going to create a cycle, right? So let me get rid of that edge. What is the cheapest other edge in the graph that I can add? Still 4. I didn't add this one, right? Now what's the cheapest edge that I can add? 5. This one is good. Notice that the world is disconnected. Okay, that's fine. Prim's algorithm was starting at one point and growing out. Kruskal's is searching through the all set of edges every iteration. What is the next cheapest edge we haven't considered? Well, we didn't consider the 5 over here, but that one is between two vertices that are already in a connected component, right? It creates a cycle, so that's bad. Now I can add an edge of 7. I don't like this one because it creates a cycle. Which one of the other two 7s can I add to create the minimum spanning tree? Should I add a green one or a red one? Doesn't make much difference. It depends whether you like green or red better. Okay? Who likes green better? Who likes red better? Everybody seems to like red better, so let's add that one. Okay? Does everybody see that we could have added the other 7 and the whole graph would still be connected? Okay? So on ties we get choices, right? That's why there can be many different minimum spanning trees. Okay? And this is what I got for Kruskal's algorithm. You'll notice that my Kruskal algorithm gave me a different algorithm, a size tree, than a different tree than the Prim's algorithm. Why could Kruskal give me a different algorithm than Prim's, even though they are both minimum spanning trees? If I'm trying to find the minimum spanning tree, why could they give me different trees? Yeah? Because the edges would be the same total weight, right? If I take a look at this one, what's the cost of this one? I did a bad job adding it up last class, but I believe that that's 2, 2, 3, 4, 5, 7. That was Kruskal. And when the Prim's algorithm, we started here. Grow, that was 5. Grow, that was 7. Grow, that was 3. Grow, that was 2, 2. And grow, that was 4. So I believe I've got a 2 and a 2, and a 2 and a 2, a 4 and a 4, a 3 and a 3, a 5 and a 5 and a 7 and a 7. Okay? Different trees, same weight. Okay? And actually exactly same set of edge weights in the tree. Okay? Any questions about that? Yes?
We tried a Prim's algorithm at the far upper right point. Will we get the same?
You mean, what if I did Prim's at a different vertex? Is that what you're asking? Well, Prim's algorithm is correct regardless of what vertex you get. Will I get a different tree? Okay, I might get the same tree as that Kruskal one, but there's no reason why I have to be able to get a Kruskal tree from a run of Prim's algorithm. Think about a world where all the edges, it was a complete graph, and every edge was of weight 1. Then any spanning tree of 1 would have the same weight as any other spanning tree. Okay? And so there's a great freedom for the things to break ties in the same way. Now what you may be saying is, if, however, all the edge weights were unique, then there would only be one way to put the tree together. And then they would find exactly the same tree. Okay? Any questions about that? Okay? So that's Kruskal's algorithm. Any questions? For what it's worth, I had Kruskal in an algorithms class, Kruskal's son in an algorithms class when I was in grad school. Doesn't make much difference, but that's true. Okay, why is Kruskal's algorithm correct? Okay, you need the same kind of an idea of a proof by contradiction. Okay, if Kruskal's algorithm is not correct, what does that mean? Well, there must be some example where it's not giving you the minimum cost spanning tree. I'll say, oh, let's run Kruskal's algorithm on this. And what are we going to do if these are the vertices? Kruskal is going to go happily adding short edge, short edge, short, and you're going to tell me, what do you mean? This is where you went wrong. This edge, you cannot add this edge to the ones you've already picked and get a minimum spanning tree. And I'm going to say, oh, okay. Why don't you then show me the minimum spanning tree? It's going to include those blue edges. It's going to include other black edges, other edges. Maybe it'll include this and this. Maybe it'll include this and this. If I add if the black and blue edges, now the black edges, form what you tell me the minimum spanning tree is. And I'm going to say, oh, actually I should leave the color. Let me get the colors back. This was in, this was in. When I added this edge, okay, if I add this edge to what you tell me the minimum spanning tree is, I am going to create a cycle. Is that right? Now, I claim this edge is not going to be the heaviest edge on the cycle. Why not? Well, when I added this edge, it did not create a cycle with what I already had, because otherwise I wouldn't have added it, right? That means that there is at least one other edge that was added after I added this edge. What do I know about that edge? Right? Remember what's happening. I'm adding edges. Ka-chunk, 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 and you tell me that's where I went bad. Well, I'm going to put that one in, and now say, show me the other edges you added. That plus my red edge is going to create a cycle. How do I know that that red edge is not the heaviest edge on the cycle? This is what the critical issue is for proving Kruskal's correct. If it was at all possible that red was the heaviest edge on the cycle, then what you had was a minimum spanning tree without me. Why do I know that red cannot be the heaviest edge on the cycle? Yeah?
You're adding another edge. You're adding an edge after that isn't the red edge?
Because these edges, the black edges, would have been picked by Kruskal's algorithm after the red edge, right? Why would an edge be considered after the red edge by Kruskal's algorithm? Only if the weight was bigger than, greater than or equal to the weight of the red edge. So therefore I could delete any one of these black edges and add the red edge and get a spanning tree that was as small or smaller than what you tell me the minimum spanning tree is. And that's what the contradiction is. Okay? Any questions about that reasoning? That is the reasoning why Kruskal's algorithm is correct. Any questions one way or another? Okay? This is important to understand, because again, the miracle of these minimum spanning tree algorithms is that the greedy algorithm works. Okay? Almost nowhere in life does the greedy algorithm work. Does it guarantee the correct thing? Again, this was the idea. When I added that extra edge, if you tell me that's wrong, I am going to add that to what tree edges you had. All the edges that were not in that cycle yet, okay, are going to be bigger than the one I just added, that had not been added yet, okay, which in this case would look like they would have been this one, this one, this one, and this one. All of those have to be at least as big as this, because Kruskal was adding them from smallest to biggest. Okay? Any questions? Okay? So you should know, it's important to me that you know why Kruskal's algorithm is always correct. Okay? Any questions? Now, what is the running time of Kruskal's algorithm? Okay? First thing we need to do is to consider the edges from smallest to biggest. That to me means sort the edges. Okay, so suppose I sort the edges. If I have m edges, remember it's a sparse graph, it's got n vertices and m edges. If I sort it, it will take m log m time. Okay? Now what if it's a dense graph? What if it in fact has a quadratic number of edges? What would be the time that this sorting would take? If I have a dense graph with a quadratic number of edges, what is the time, running time in terms of n? Just doing the sorting? N squared log n. Does everybody see that even at this point I'm screwed compared to Prim's algorithm if my graph is dense? Okay? So we're talking about Kruskal's algorithm is good for sparse graphs. What is it that I've got to do? I'm going to take each edge at a time, and I'm going to want to know as I add edge UV, okay, does it create a cycle? Okay, you kind of get that idea? I've got a graph that I'm building up. I want to know if I add edge UV, does it create a cycle? How can I figure that out? Okay? Does everybody see what I'm kind of doing? I'm building my graph incrementally. Edge, 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 edge. The critical thing is, does adding this edge create a cycle? Okay? How would I be able to tell that? Okay, can someone give me a test? Maybe slow, but given the edges currently in my tree and my new edge, how can I tell if that new edge created a cycle? Yeah? Can I do what I did before and what? I could keep track of a parent. Okay, what do you think? Well, it's a little tricky. How would I know? You want me to keep track of something. Like whether the vertices are in the tree, but notice this vertex V is already in the tree, I have edges on it, right? On this vertex, I already have edges on it. Did they create a cycle? It wouldn't help to create a cycle. Why? Because they are not in the same connected component. Does everybody see that that's kind of what the issue is here? Okay, as I add edges, I'm going to be shrinking my number of connected components. In an empty graph, bunk, 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 every vertex is in its own component. Every time I add an edge, I reduce my number of connected components. Okay? Maybe I'm going to reduce it by just adding a vertex to an existing one, or I'm going to be taking two big components and adding them. Right? So the real question is whether or not the two endpoints are in the same connected component. How can I tell if two edges are in this connected component? What? Do a DFS is a perfectly fine thing. So one way to do it is I go run a connected components algorithm, which took time order n plus m. And that would have told me m for the number of edges in that graph, okay? Which in this case is the tree we're building. And then I could tell whether the two vertices I want are in the same component, okay? Given that I'm building a tree, the number of edges in my tree is going to be order n. So my claim would be that doing the connected component test would take order n time per each iteration. So one thing that I could do is say, find all the connected components in the subset of minimum spanning tree edges, and then tell me whether I and j are in the same component. That would take order n. Another way would be to add the candidate edge to my graph and then do a depth first search and see if I get any back edges. If there's going to be a cycle, there's going to be a back edge. So that would be a way of telling if I caused any trouble. Both of those would take order n. So what is this going to do? For each one of the edges in the graph, of which there are m of them, I could just, with the routine implementation, I could, in order n time, find whether or not that edge is going to create a cycle, and if it does create a cycle, I discard it, otherwise I add that edge. Okay, any questions about that? What would be the running time of this algorithm, this part of the algorithm? Done using that, if we're doing that connectivity on every possible edge insertion, what is that total running time of this part going to be? Someone loud. What's the running time going to be? M times n. Okay? Are we happy about this? We are not happy about this. We know how to do it in n times n, right? Okay, so this doesn't look like the implementation we want. In order to do this faster, we need to find a quicker algorithm to tell whether or not something is going to be creating a cycle. We need a data structure that is going to let us do that test faster. Any questions about that? Do you see kind of what the reasoning is? Okay? Any questions? Okay? So what you should believe now is Kruskal's algorithm is correct. Okay? And if I could find a faster way to tell whether two vertices are in the same connected component, okay, then if I had a data structure that would tell me that quickly, okay, then if I could do it, let's say, if I could do this in log n time, what would the time of Kruskal's algorithm be? This would be m log n, okay? What would the first part be? It's m log m, okay? What is which is bigger? What is the sum of m log m and m log n? What is the sum of that in a big O sense? Which is bigger typically, n or m? M, the number of edges, right? So does that mean that this dominates the running time or this? It looks like this dominates the running time, but let me show you a little trick. What is the biggest that m can be? What is the biggest in terms of n that m can be? N squared. What is m times log of n squared? What is the log of n squared? Does anyone know how to take what the log of n squared is? You pull the exponent out, that thing is going to be equal to m times 2 times log n. Right? So the truth is both of these are going to be m log n. If we can find a logarithmic time way of finding the whether or not there's a cycle created. Okay? Any questions about that? Okay. Sorry, this is going to take longer to erase because I did a lot of that stuff there. So for this to work, I've got to show you a faster way, a data structure that would ideally in logarithmic time keep track of what you call whether two things are in the same component. Okay? So I claim that I'm going to want a data structure that can do two different things. Given vertex v and y, v1 and v2, tell me, are v1 and v2 in the same component? And if they're not, merge the two components. Okay, so I'm going to give you a vertex v1 in component c1 and a vertex v1, 2 in c2. Merge those components together. Okay, if I could have a data structure that could do both of those operations quickly, then I would be golden. Does everybody see that? How can I build a data structure that does one of these things quickly? Okay? What if for every vertex, v1 through vn, I keep track of what component it is in? Right? If I assign every component a number, does everybody agree? If this is in component 1, 2, 2, 3, 1, if I want to know, does this vertex in the same component as that one? All I've got to do is to compare, if I have an array C with the component number, how much time will it take to tell whether they're in the same component? Constant time, that's great. How will, if I decide that I want to merge components 1 and 2, that's the second operation, right? How would I go about merging all the components 1 and 2? What would I like to do? If I went through this array and I changed every 2 to a 1, does everybody agree that now the components are merged? Okay? What is the running time of this operation? O of n. So I'm not yet happy. Does everybody agree that with this implementation I could do it that part in O of 1, but this part is linear? Okay, I need to be smarter. Okay? Any questions about that? Before I show you smart, you should appreciate why there's a problem. Okay, any questions about that? The smarter idea is a data structure called union find that I want to go through fairly quickly. But it's a cool thing, and it's occasionally a very useful thing outside of minimum spanning trees. Okay? Again, basically the way that we would want, our minimum spanning tree is basically put the edges in a heap or sort them. Doesn't make any difference because this is going to dominate it. While the count is greater than or equal to, well, the count is less than n minus 1, meaning we haven't brought all vertices in. Take the next smallest edge. If it's not in the same component, add it in the tree and merge the components around. And if we could do the component merge and test in log n, then we are golden. Okay? What is the data structure that we're going to use? The union find data structure. Okay? Actually, let me show you an example. What we are going to do now is represent components by what we will call union find trees. Now, why am I calling them trees and not trees? Well, these are directed things where all edges are going to go towards the root. Okay? What am I going to do? I am going to represent each component of the graph by a tree, a tree where every vertex has a parent except the root of the tree. That's what we've seen before, right? We're going to say the name of the component is the ultimate root of the tree. Okay? So what is the idea here? If we have for one of these things, and we want to know whether two vertices are in the same component, how can we find out whether 6 and 7 are in the same connected component? What do we got to do? We're going to start from the first one and walk up the parent thing until we find the root. And we're going to start from the second one and walk up on it until we find the root. Does everybody see that? Now, how do we know if they are in the same connected component? Okay. If we find the root of the trees that they're in, and if they're the same, they're in the same component. If they are different, then they are in different components. Okay? Any questions? Okay? What is the running time of that test going to be? What is the running time of finding out what my root is? How much time? I think I'm hearing something, but my hearing is bad. What am I hearing? I'm hearing what? Log of n. Well, it would be log of n if the height of the tree was log n. Does everybody see that it depends upon the height of this tree? If the tree looked like this, goes to that, goes to that, goes to that, goes to that, goes to that. Does everybody see the height could be order n, unless I do something to keep it short, right? What is it, how do I merge two of these components? Suppose I've decided I want to merge two of these components. What should I do? I want to make it so that the people in the second component have the same root as all of these guys. Does everybody see that it's just a matter of taking the root of this one and pointing to the root of that one? If I do that, now they are all in the same component, right? And only one pointer had to change. And now, woof, they're in the same tree. Okay? Any questions about that? So the great thing is that in principle, once I have the roots, once I've done a find, the merger of these things can take constant time. Okay? Any questions? Now here's a question. Am I better off having, if I decide I want to merge 4 with 3, am I better off having 4 point to 3 or 3 point to 2? Does everybody agree that doing either the blue merge or the red merge would end up accomplishing exactly the same thing? Right? Which one of these is better, blue or red? Is there anything to speak to in favor of one or the other? Yeah? Does everybody see that the height of this thing was 2? The height of this thing was 1. If I made if I picked the red edge, all of these nodes, the height of this thing is going to increase to 3, right? If, on the other hand, I pick the blue edge, the height of this goes to 2. Does everybody see the maximum depth did not change? Okay? So what do I want to do? I want to have the shorter tree point to the taller tree. Okay, so I don't increase the height. Okay? And while it's hard to do exactly that, what if for every node I keep track of the number of nodes in it? This one has 4, this one has 1, this one has 2. What if I always have the bigger one, the smaller one, point to the bigger one? Does everybody see that? The height of the bigger one is never going to change. Right? What is the only time when the height of the biggest tree is going to change with such a merger? What happens if I had 2 trees with the same number of nodes? What happened if this tree had 5 nodes and this tree had 5 nodes? Which one should I make be the root? Okay, I can't benefit one or the other, right? Which one should I choose? Well, whatever one I choose, these guys now have a taller path. Right? But how many mergers can I have like that? Well, notice what happened to the size of the tree if they both had the same number of nodes in it. What happened to the size of the tree? It went from 5 to twice 5, right? It doubled. How many times can I double things until I get to the full node, to every node in the tree? What I heard, log n? Why is it log n? Because log n is the number of times you can double something till you get to log n. Okay? So if I use a little care and always put the smaller tree as the pointing to the bigger tree on a merge, the height is going to increase only when the nodes double, and the nodes can double at most log n times. Any questions about that? So implement, yes?
So you're saying just keep track of the number of nodes in each component, and we always just combine less nodes to the one.
Exactly right. The one with less nodes becomes the vassal of the guy with more nodes.
What about the instance, let's say we have one component with 100 nodes and the other with 1,000, but the one with 100 nodes is just like a line straight down?
Okay, well, you're saying, what if we had one with 100 nodes that looked like this? Notice that the only way you're building these things is by unioning components. How would you get a component like that? Well, at the beginning, they all started out in separate components, right? Sorry about this. Ka-chunk, ka-chunk, ka-chunk. You added an edge, and now I've got something of like that. I'm now going to merge, let's say I want to merge this guy in, some other vertex in. What's going to happen? Am I going to put this red one on top? No, that's the smaller component. I am going to do that with it, right? So the answer is I could not, that if I do this policy, I will never get this long skinny thing. The only way I'm going to do a merge is if the small guy merges to the big guy, or or merger of equals. Okay? So the height only occurs on the increases on a merger of equals. Any questions about that? This is kind of clever. Okay? But once you see that, you can now do Kruskal's algorithm in m log m n time. Okay? Which is good for sparse graphs. And this kind of set union data structure I'm talking about is a useful thing when it comes to certain clustering kinds of things, right? If originally none of you are in a club, but slowly you form disjoint clubs, okay? Eventually clubs may merge, but you can never leave a club. Notice there's no way we can delete edges from this thing very easily. Okay, this is only if we're going to be doing merging, okay, and asking what club you're in. Any questions? Any questions about Kruskal's algorithm? I'm not going to, the details you can read about in the book, or see what I did there, okay? Actually, let me look at maybe I can show you the Kruskal's code. I think, do I have a code for this? I'm a little bit confused about that. Never mind, maybe I don't have the code here. It's in the book, but it was pretty obvious. Sort, and then do this, keep taking the next smallest edge. If it didn't create a cycle, edit, and then merge the components. Okay, any questions about Kruskal's algorithm? Okay, I am now going to, so now we know about minimum spanning trees. We know about two different ways to build minimum spanning trees. We know about a lot of things. What I'd like to talk to you about is maybe the weighted graph problem that you have seen probably more than any other one, or it comes to mind most obviously, is the problem of finding the shortest path in a graph. Actually, I guess I don't have a slide for that. Okay? So you can imagine that you're given a weighted graph. If it was the road network, the question that you would really like to know is, what is the shortest way for me to get between here and Poughkeepsie? Okay? That is finding a shortest path in a road network. And there are a lot of different problems finding the shortest path between two nodes in a graph clearly comes up in transportation problems. It clearly comes up in communications problems. In a network, you want to get the message from point A to point B. How do you route it? The way that should take the smallest amount of time. Okay? So finding shortest paths in graphs are important problems. And maybe next time, if I remember, I'm going to show you a good application of finding shortest paths. How do you find the shortest path in an unweighted graph? Okay? We talked about this. If I have an unweighted graph, okay, where all the edges are of weight 1, how do I find the shortest path from X to Y? Have we discussed anything that does that? Yeah? Breadth first search. So if I want to find the shortest path in an unweighted graph, I start from this vertex. Find everything that's one hop from me. Then I find everything that's one hop from things that are one hop from me, which means they're two hops from me. Find everything that's one hop from something that's two hops from me. That means it's three hops from me. Okay? So the good thing is that breadth first search in an unweighted graph finds the shortest path. Okay? The trouble comes when we have a weighted graph. Okay? I mean, a breadth first search is great. Note that on a weighted graph, Okay? Breadth-first search will still find the path from X to Y using the smallest number of edges. That kind of corresponds to the weighted drive from here to there using the minimum number of turns. Okay? But you have probably had situations like this, where maybe you have a world where there's a road, a long road, and then you make a turn here and you can get from X to Y. There might alternately be a way to get there. Using a lot of little edges, right? Breadth-first search will say the red path was cheapest because it's ignoring the weights of the edges. If the edges can have bigger, if the edges can be big or short, a path that uses a small number of big edges can be longer than one that uses a large number of short edges. Okay? And we get into a world where, so there's a limit to how far breadth-first search will help us when we try to find the best possible path. Okay? Any questions about that? Let me show you something else that's weird about finding shortest paths in a, in a graph. Is what happens if we have negative weight edges. Let's say you want to find the shortest way to get from New York to let's say San Francisco, where my favorite baseball team, the Giants, are playing tonight for the championship. Suppose I want to get out there to see it. What is the fastest way to get to San Francisco? What if I told you that in Chicago there was a time machine, okay, that would a road, it was like an ATM, you drove through this thing, and it got you there, and it set the clock back an hour. Okay? Suppose it was negative time. You go through this road in Chicago, and the time goes backwards by an hour. Right? What is the cheapest way to get from, let's put it in Florida, so we know that it's all the way out of the way. The real normal, if all the edges were positive, the cheapest way to get to from New York to San Francisco would not go through Florida, right? But what if we had a world where in Florida there was an edge that cost minus 100, and it took 3 minutes to drive there, 2 minutes to drive there, and you got the clock went back by 100. Whenever you went through that edge, what would be the cheapest way to drive from here, New York to San Francisco? It would involve driving from New York to Florida, getting into this phantom loop, and going through it 1 billion times. Does everybody see what's going to happen here? You're going backwards. It's back to the time of the dinosaurs. Back to the time of the Earth's creation. Does everybody see what the problem is? What's the shortest path from New York to San Francisco if you have negative cost cycles? It's infinitely small and you never reach there. Does everybody kind of get that idea?